In our last video, we talked about how a concrete problem may be sometimes made simpler if we move to an abstract version of the same problem. Now we use that in our everyday life all along. The examples that I gave you are somewhat uncommon. You really do not count pillars and you really do not parade a soldier like that. But here is a very practical example. Suppose you are collecting money from different people and the first guy gives you 73 rupees, the next one gives you 19 rupees, then 5 rupees and 25 rupees. So you make a note of all these amounts on a piece of paper. You want to find out what is the total number or what is the total amount that you have. Now if you treat it as a concrete problem, then you have 73, then you get 19, so you will add 73 plus 19. After that you get 5, 73 plus 19 plus 5 plus 25 in this order. But if you are given this sum, most of us will not proceed in that way. Instead, we will quickly observe that certain parts are easier to add. You will quickly notice that this 5 plus 25 is 30. And the moment we see that 30 here and something 70-ish here, we will quickly add these two things and get 103. This 103 we will split up mentally as actually it is 100 plus 3. So you keep the 100 aside. We are always uncomfortable adding large numbers. So we keep that 100 aside. 3 and we will add 3 with 19, which is pretty easily done, to get 22. Bring that 100 back and the answer will be 122. In fact, most of us will do this addition much faster mentally than adding just the first two numbers because they are kind of ugly looking numbers. Notice that what we did here is actually an application of abstract algebra. The concrete version said that these numbers are amounts of money, they are coming chronologically in this order. So when you say 30, this 30 is an abstract quantity. 30 was never the amount of money in your pocket because before this came, these things were already present in your pocket. So 30 is an abstract quantity that is meaningless with respect to the problem that you were solving. Similarly, this 103, you split it up and 100 plus 3, added 3 with 19. This 3 was never there. No one gave you an amount of 3. Why did you add 3 with 19? The 22 is an abstract quantity. All that you know is that the final answer, 122, is the same as the answer that you would have obtained had you followed the concrete path. So this was the concrete thing, and to which you had 122 in that brute force way. You took a roundabout path where each of the intermediate steps were easier. These intermediate results were meaningless. However, the final thing is the same. So instead of following this concrete path, we prefer to follow this abstract path. Now this is possible because we know certain useful properties of our everyday addition. Namely, even though we were asked to add them in this order, we can actually remove the brackets and add them in any other order. Certain other orders are more beneficial for us. Similarly, whenever we want to do any kind of binary operation, it helps if the binary operation is flexible in such senses so that you can do things in a different way than what is dictated by the concrete method. If that is not the case, then abstraction typically will not have any benefit. If you have to follow the procedure of the concrete method, that is the only way of doing it, then why care about doing abstraction? Abstraction helps only when you are allowed to do manipulations. The very first thing that you need in order to break away from the shackles of your concrete setup is associativity. When I give you some binary operation, say A and B, like the addition, and I ask you to do this, What do I mean by that? By this I mean you first do this and then you do that. Like the money is coming one by one. So first do this, because it's always like an algorithm. You first do this, then you do this, then you do this, then you do this. The point is, I do not really want to carry out all the steps one by one by one. The very first thing that I have to make sure that these brackets are not that important. Because as long as these brackets are there, I am forced to do this first and then this next. So I would like to have at least, I should have the freedom to do this part. That should not matter. If even this is not true, then abstract algebra will typically be quite useless. So this binary operation then will not give you any benefit of abstraction. So you naturally want this thing to hold, and you want this to hold for all A, B, C. So whatever type of object you are combining with your binary operation, you should have at least this freedom. Instead of combining this first, I am allowed to combine this first, because then even though this may not make any sense in your concrete problem, at least I am guaranteed that the answer will be the same, and maybe in certain cases this will be easier to do. So that is the very first thing. If it is not associative, it's not worth abstracting, because you can't do any abstraction. You will be just stuck with your concrete version. The next thing is commutative. When I did this, 7 plus 26 plus 3, we typically say, hey, add 7 and 3 first, 10 and 26 is 36. We do not usually add this and this and get, I do not usually do that, so get 33 plus 3, because we find this a little bit more difficult to do than 7 plus 3. How would you do that? Actually, you did two things. First of all, you were asked to do it in this way. You broke away from that. You said, I can do this, but even that will not bring 7 and 3 together. You swapped. The fact that if you add this with this is same as adding that with this, that helps. And that is commutativity. That means if you are given any two things, then there should be A star B is B star A should better hold for all AB. So this is the very first step that makes you free, and this is one way of making use of that freedom. Now you can combine something with something else which is far away, bring that closer, and that will make your life easier. The next property that we are considering is called closure. In fact, in a sense, it should be the 0th property in the list. It is kind of trivial. So whenever we are working with any abstract situation, we are basically working with a set of objects that we can combine in some way. For example, in a parading soldier example, the set was left, right, about turn, and halt. And the way we are combining was the followed by operator. So when I said L followed by A, that means left, then about turn, that is right. So this was the followed by operation. L followed by A was R. So what is meant by saying that this is a binary operation on S? This means take any two elements of S, combine them using star, and you will get another element of S. Mathematically, star is like a function which takes two elements of S, so it takes a pair of elements of S, that is S cross S, to S. Like if I say 5 plus 3 is equal to 8, I might as well think that plus is a function, call it add, 5, 3 is equal to 8. So 5, 3, this pair is an element of my set S cross S. So S in this case may be set of all integers. Now if this gives you something that is outside S, or gives you something which doesn't just exist, is undefined, then naturally it is not even a binary operation. That property is called closure, that at least given two elements of S, if you apply star with it, it will still be in S. So that is kind of a very trivial condition. If this is not the case, it is not even a binary operation. So by closure, we mean the following. For all A, B in S, whatever is the set, A star B should better be in S. Now, this is very trivial. In most cases, this will be satisfied. And because this is already part of the definition of a binary operation, most standard textbooks will not list it as a separate property. They will merely say that let star be a binary operation on S, and they will understand this condition by that. But there are certain situations where we need to check it explicitly. For example, you know that addition is a binary operation on set of all integers. Now, if you think wrongly that if, say, S is the set of all odd integers, then consider the binary operation addition on set of all odd integers. You might say, oh, there is no problem with it because odd integers can also be added. Yes, I can add 3 plus 5. So this is a meaningful thing. So addition must be a binary operation defined on S. But that is not true. Binary operation doesn't simply mean that you can add them. The fact that the sum must also be in S is important. So if I add, I will get 8, which is not in S anymore. So plus is not a binary operation on S, or we may say that plus violates the closure property. More commonly we say that S is not closed under addition. S is not closed under addition. Now, unlike associativity and commutativity, which are there to make your life simple, closure is basically part of the problem itself. If it is not closed, then we are just making a meaningless statement. So, closure is kind of a sanity check. It doesn't make your life easier, it just makes the problem meaningful. So, closure is sort of the zeroth property. Suppose I am to make a picture. I want to draw a picture and I am not a very expert artist. So I want to draw a picture like this. I want to draw a face. This. Oh, no. That is wrong. What do I do with that? So if you see that you have drawn something badly, you do some erasing. Now, had I drawn it using a permanent marker, I would not be able to do this erasing. And that will make life so very difficult. The moment you make a mistake, you have to throw this away entirely, all the good things that you have also done, and start again from scratch. So when a novice artist like myself will draw, we prefer to use erasable markers or pencils with eraser and things like that. That is, we want to be able to cancel whatever we have done. That is why pencils come equipped with erasers. If you are a novice artist, you never try to draw directly with a pen. Mistakes cannot be erased. So I had this situation, then I went to this and I said, oh, it is bad. I erased and I went back to wherever I was. This is a very useful thing to have for any binary operation. You should be able to go back. All the routes are two-way. If you can go, you can come back also. Thus, if I have A star B and I want to recover A from that, you should be able to apply one more step to come back. So, if I write something which I will call B inverse, then I should be able to come back to A. Had that not been the case, such a binary operation is really difficult to work with. Just imagine that you are moving through a maze, or you have come to a big house, there are lots of doors and lots of corridors, and you are trying to find your place. That is difficult by itself. Now, how much more difficult it will be if whenever you pass through a door, the door just automatically closes behind you so that you cannot go back. That will be really scary, right? But at least if you have the satisfaction that if I make a wrong move, I can at least retrace my step and get back to where I was. But if you are not allowed to do that, then that will be scary. Similarly, a binary operation without inverse is a scary thing to use, just like trying to make a sketch with a pen. If you make a mistake, it becomes permanent. Now, in order to define inverse, we have to be little careful, and we need something whose presence initially does not seem to be that well motivated. That is called an identity. Identity simply means something which does not change. Like if I have 5, I add with it 0, I get 5. And it is not a special property of 5, it's a special property of 0. Similarly, if I take any number and I multiply this with 1, it remains itself. So addition by 0, multiplying by 1, these things do not change. In fact, that is why people had a really tough time to even accept 0 as a number, because it does not do anything. So why should I really call it a number? That was a big conceptual step. Now, whenever we want to work with an abstract function, some binary operation, we want to have inverse, and as a first step, we should better have an identity. Not that all binary operations have them, but if they have, it's nice. For example, in my that parading soldier example, I had that halt command. You may have wondered, why did I have the halt command? It said, don't do anything, but that helped. In the triangle example, I had an E command. E said that do not do anything. These do not do anything are important because they provide identity. By themselves, they are nothing very great, but they are the first step towards this very useful thing called inverse. So here is the definition of identity. I have a binary operation star acting on a set S, then by identity I mean some element E in S such that if you apply that binary operation with that element, nothing changes. So whatever A you take, A star E is A. And remember, I have not said that the binary operation is commutative, so I need to separately write down E star A is equal to A. If that is the case, then we say that it is an identity element. Now, it is not very difficult to see that identity element, if it exists in an associative setup, then that has to be, if the binary operation is associative, that has to be unique also, but we will postpone those properties to the next thing. So for the time being, it is an identity. Now, as I said, identity by itself doesn't do much. You may be wondering why keep something which does not change, and the main reason is inverse. So I will say that A in S has inverse element, which I will denote as A inverse, again another element in the set S, if A star A inverse is identity. That means you have done this and you have done its opposite, then together they cancel off and you get back to your blank page, your initial configuration, doing nothing situation. And of course you need the other way also, because I have not assumed commutativity, so it is this. Now I have not put a for all here. If that is the case, I will be very happy, because then every element has inverse. But it is quite possible that certain elements have inverse and certain others do not have. So if some A has this thing, I will say A has an inverse, or A is invertible. So inverse, or we'll call A invertible. So these are basically all the properties that we expect from our binary operation. More properties it satisfies, the more easy it is to message it in abstract ways, and hope that we'll get easier and easier shortcuts to arrive at the same result required by the concrete method. If less and less properties are satisfied, we have less and less hope from our abstract method.